Good afternoon. I'm Phil Simpson from Lattice Semiconductor, and I'm here with Khalid Khan from Synopsys to talk to you about team-based design. In today's presentation, Khalid will provide a quick overview of the Synopsys tools for FPGA design, and then we're going to move on to the topic of team-based design, where we'll talk about the benefits, challenges, and guidelines in implementing a team-based design environment. Then Khalid will come back and present further on the Synopsys high reliability solutions that are applicable to specific use cases of team-based design. And then we'll have the final summary and open it up to questions and answers. But first, a few introductions. So I'm Phil Simpson. I'm the Director of Tools Marketing at Lattice Semiconductor. I've been working with FPGAs for a little over 30 years, starting as a design engineer, progressing through applications engineering, and now into my role as Strategic Marketing Director, where I define the roadmap for the FPGA design tools flow at Lattice. Prior to Lattice, I spent considerable time working at Altera and Intel, where I worked on FPGA design flow definition and published the Springer book on team-based FPGA design, as well as co-authoring an article, award-winning article at SNUG conference on design reduce in FPGAs. I will now hand you over to Khalid Khan, who will do his introduction.
Hello, everyone. My name is Khalid Khan. I'm an application engineer with FPGA synthesis and prototyping team at Synopsys. I'm based out of Synopsys headquarters in Sunnyvale, California. I provide support to major accounts within the West Coast region and also drive the simplified product roadmap and new features. In this presentation, I'll go over simplified safety and high reliability features for FPGA synthesis design. Simplify is widely adopted synthesis solution with leading synthesis innovation for 25 plus years. It is the most common FPGA synthesis engine for many FPGA vendors, including Lattice Semiconductor. It is timing-driven synthesis tool that provides best in QR features with high performance, small area with advanced synthesis technology. Simplify also provides broad language support, such as VHDL 2008, 2019, as well as Verilog and System Verilog standard. Fastest runtime with max parallel jobs using the distributed compile and distributed synthesis features. Find and fix bugs early in the design cycle with Synopsys verification family of products. Fastest design bring up and debug turnaround with real-time hardware signal capture for waveform viewing. Versatile IP handling with various encryption formats, such as IEEE 1735, Synopsys proprietary SYNINC, and designer IP encryption, as well as support for latest and legacy FPGA device families. Simplify also provides best-in-class automation of safety and high reliability features for mission-critical FPGA designs. This includes features such as automatic error detection and mitigation insertion, triplicate logic with physical separation, duplicate with compare, Hamming tree for FSM, and arbitrary fault injection for debug and verification. Next slide, Phil. Synopsys FPGA verification flow and easy design bring up. To address verification of functional safety and help identify design issues early in the design cycle, Synopsys provides tightly integrated family of FPGA verification products that enable users to meet functional safety and high reliability goals. At the center of it, Simplify, as best-in-class synthesis engine with automated logic insertion features for functional safety and high reliability. Spyglass provides statics verification with RTL level length checks and clock domain and reset domain clock crossing violation checks. Euclid is a comprehensive RTL IDE environment that provides on-the-fly language syntax and language rule checks. It also provides auto-completion and auto-insertion of RTL blocks for simulation and verification flows. VCS provides the fastest, the most accurate, and high reliable simulation tool in the market. Simplify auto-generates VCS simulation scripts for RTL, post-synthesis, and post-placement route netlist to easily bring up the simulation environment and run it within the Simplify project environment. Simplify also provides integrated hardware debug environment with Identify and Verdi debug tools. Identify instrumental debugger tool provides easy-to-use interface to probe any hierarchical design signal and dump out waveform from live hardware. And Verdi debug environment allows users to compare waveforms and correlate live hardware signal values back to the original RTL signals for comparison and verification purposes. Back to you, Phil.
Great. Thanks very much, Khaled. So now let's talk a little bit about team-based design. So there are many disciplines involved in the design of a system with an FPGA in it, ranging from board designers to signal integrity engineers. If you've got an embedded soft processor, you will have embedded software engineers and potentially a separate verification team. Now, typically there will be an FPGA design team lead that will coordinate the transfer of data across the different disciplines to complete the design. On typical mid-range FPGA designs, such as designs targeting the Avant family, there'll normally be several RTL designers working on the design, and they'll be specialized in particular functional areas such as PCIe Express implementation or perhaps a particular type of DSP algorithm or waveform. These engineers are responsible for developing and closing timing on those particular design blocks for the FPGA. The team lead who is responsible for the integration of these design blocks into the complete system FPGA design. So he'll work with those engineers in resolving any integration issues from a functional nature or from a timing closure perspective. In this presentation, we're mainly going to focus on the RTL, the bit stream flow of FPGA design from a team-based design perspective. So, what are some of the benefits of FPGA-based design environment? The main benefit is that the design can be completed much faster. You have multiple engineers that can work concurrently on the majority of the design, thus reducing the design cycle, particularly when these engineers can focus on their area of functional expertise. It can also help with achieving repeatable results from compile to compile, as it can enable the preservation of results for the design blocks that have been completed when you put in place the block-based or macro-based design flow. If you implement this type of flow with scripts, it improves the repeatability, but it also helps in the transfer of information in the design environment as other engineers may be brought on or take over the project. For certain types of applications, it really is a must-have capability. An example of this would be safety critical applications, which we'll talk about later in the presentation. Now, there are some unique challenges to implementing a block-based design environment for FPGAs. Some of these can be the floor planning of the design. Some of them can be ensuring the design has been partitioned successfully for timing closure and to get the maximum device utilization. Within this presentation, we're going to provide some details on the techniques that can help them navigate through these challenges to make the experience successful. So let's start looking a little bit about the use case of an isolation design flow. So in the safety critical or isolation design flow, the secure area of the design is shown in this diagram in yellow, only contains logic for the secure design block. In an isolation flow, there's also a barrier or a moat around this area where there would be no logic present at all. The goal of the secure block is to keep it away from the rest of the design. So only the placement and writing of the secure block would be maintained in that yellow area. And the only other parts of the design that would interface to that area would be the ports that have been defined in the RTL from the rest of the design to and from the secure block, and any of the control signals such as clock and reset lines. The user will, typically a single user will work on that secure block. He will implement it in the floor plan constraints. It closes timing. If the user has met their timing requirements, hopefully with margin of 10 to 20%, they will then lock the place and route. And then this locked place and route will be used in the project for the rest of the compiles where the rest of the logic may still be developed or may still be changing. So one of the key aspects here is floor planning and closing timing. So how do we address some of the challenges in architecting an FPGA design for team-based design? So the partitioning of the design really can make a difference between success or a lot of work with the FPGA design because it impacts timing closure. It can also impact the device utilization that you can achieve and effectively the efficiency of the engineers. So for engineering efficiency, it's really best to partition along functional boundaries so that engineers can focus on their area of expertise. It's also recommended that you try to maintain critical paths within a single partition. And the best way to achieve this is by registering the inputs and outputs to the blocks, as well as avoiding the insertion of logic between the interface of multiple partitions. It is also much easier to partition between modules by having fewer connections between the modules, so try to minimize the number of signals between the blocks. This gives more flexibility for the writer to have more choices of writing and to be able to ensure that there isn't a critical path due to writing between the blocks. And then finally, the size of the macro is important. It's really best not to have a macro that is too small in a few thousand logic cells. In some applications, such as the secure, it may be that the application demands that you have a small partition or block, but generally having a bigger partition and having fewer partitions in the design will achieve better utilization and can help with the timing closure. So now that we've discussed some of the techniques for successful team-based design, we'll now look at implementing the design flow in the tools. So we'll start with a quick look at the Lattice design tools. So Lattice provides three main tools. We've got the Lattice Diamond software, which supports the Mac X02, ECP3, 5 type families. We've got the Radiant device software that supports the Nexus platforms and the Avant platform. And we've got the Lattice Propel software that is really Lattice's embedded design suite. So this would be the interface you'd use if you were putting together an embedded system using the soft RISC-V processor. For the purposes of this presentation, we're really going to focus on this red area, designs that are put together using the Radiant tool, where Propel could be used as the embedded software interface. Now, one of the key aspects you can see here in this block is the interface between Propel and Radiant, the interface between the customer's RTL and Radiant, and the interface between the customers, between the Lattice IP and Radiant is the Simplify software. So Simplify provides the synthesis solution, and it's fully integrated as part of the flow to make it easy to put together a team-based block-based design environment. So let's look at the actual flow itself in a little more detail. The flow is really quite simple at a high level. As a designer, when you partition the design, you would define effectively the macro, which would be the partition of the design. You would start by creating a logical macro. Simplify will generate the .vm or the design netlist based on the RTL for the macro, along with the constraints files for the Radiant software. When you bring this into the Radiant software, you would then create the physical macro for the region, and then you would work with that design block and that physical constraint until you close timing and you're complete with that part of the design. And then you would export it and reuse it in subsequent compiles in the project. And the Radiant tool will export an IPM package file, which includes black box files, simulation files, etc. Now, you can also start the flow directly from within the simplified tools as opposed to starting from within Radiant. And within the simplified tools, you would define the macro along with the RTL you're using for the project. Simplify will synthesize the design to create the netlist along the macro boundaries, and it will generate the VM netlist file along with the constraint files and pass them directly into the Radiant tool. Once in the Radiant tool, this is where you would put in place the physical macro. Now, this could be fully scripted, but probably because you're looking at a floor plan constraint, the easiest way to use this is using the physical planner in Radiant, which will give you a graphical view of the floor plan. You would create the region for the macro, the appropriate empty region if you're doing the isolation flow, and you would place and write the design. Once you've closed timing and you're happy with the results, you would then export the post place and write macro for reuse in the rest of the project. Now, one tip here is before creating the physical macro, it's a good practice to actually compile the design that places the logic. And if that logic placement meets your needs and makes it easy to close timing, you would create your region around that area chip that had been previously selected by place and write. It's not necessary, but it is a good tip that can help with timing closure. So, looking at the reuse flow, now that you've placed and routed the design and you want to reuse it in subsequent compiles of the rest of the logic in the simplified tool, the simplified tool will reuse the post place and write macro through the use of black box. So effectively, this means that the macro itself would not be resynthesized in simplify. When you recompile the design, it will create the VM for the rest of the design. This will reference the black box file, which includes the post place and write macro from the Radiant tool, and then create the appropriate assignments to go back through the Radiant flow, where the Radiant software will place and write using that post place and write macro that you already had in place. So as you can see, the design flow is pretty straightforward and very well integrated, whether you start directly from Radiant into Simplify and back, or start in Simplify and come directly into Radiant. So let's take a look at a checklist. A checklist is always a good way to ensure that you're following the right processes and everybody is working on the same page. So to start with, when putting together the team-based design, you need a team lead that's going to define the design structure for the project and define the top-level project, as well as creating the appropriate partitions for the team to make design integration easy. The design flow itself can be implemented fully in the GUI, but it's really recommended that the flow is scripted for easy transfer between users and also so that the project can be handed off to other users at a later date if any updates need to be made. Individual designers will work on their particular RTL, and they should close timing on their blocks before exporting for reuse in the full system integration. We recommend that you close timing with 10 to 20% margin if possible, just to accommodate any changes in writing between blocks. And if there's any time inclusion or functional challenges, these engineers will work together with the team lead or system integrator to resolve these. Now, when it comes to secure or safety critical designs, there may be other aspects to completing the designs, such as you may want to use specific features such as TMR, triple mode redundancy on key blocks. And I'm now going to hand you over to Khaled, who will discuss some of the techniques that can be critical to these particular use cases.
Thanks, Phil. When designing any new system, safety and reliability are key factors in determining if system is safe for real-world deployment, and if there are sufficient contingency plans for worst-case scenarios. Hence, today, many electronic systems are required to meet stringent safety regulations, such as the defined by ISO 26262 standard for automated functional safety and IEC 61508 standard for industrial application, and also DO 254 design assurance guidance for airborne electronic hardware systems. Functional safety and reliability requirements are no different for FPGA-based design deployments. Today, FPGA-based designs are utilized in many safety-critical systems, such as in the military, aerospace, medical, industrial, robotics, and automotive industries, where resistance to failure is critical. Next slide, Phil. Simplify is certified for ISO 26262 functional safety certification with TÜV-SÜD safety qualification organization. We have invested in dedicated R&D resource for safety compliance and ensure Simplify qualifies for regular safety certification. Additionally, as discussed, Simplify provides many automated features for meeting safety and high reliability requirements for FPGA-based designs. Next slide. Radiation events in our atmosphere can cause unpredictable errors in electronic systems. An electromagnetic radiation or glitch can cause into register or stored in a memory element of FPGA fabric. Then it becomes a single event upset or SCU error. If this error is not detected or corrected, it can propagate into your system and potentially cause a total system failure. This is unless there's in some built-in error detection or error correction mechanism that flags the problem and takes corrective measures. As an example, if an error propagates inside a finite state machine logic, it could cause an undefined state to be reached and completely lock up the operation of a circuit controlled by the FSM. Failing to detect and correct such an issue can potentially lead to a catastrophic system failure. The good news is Simplify Synthesis tool provides safety and high reliability features that automate ways to minimize or eliminate these type of failures during logic synthesis process. Next slide. Simplify provides many functional safety mitigation techniques. For logic and register, Simplify provides local TMR, block TMR, and distributed TMR. For fault-tolerant FSM, Simplify provides Hamming tree, safe FSM, and safe case FSM feature. For memories, TMR for BRAMs, ECC RAM primitives, and error flag insertion. And for debug, Simplify provides error monitoring, fault simulation, and hardware fault injection. Next slide. Triple module redundancy or TMR techniques. Simplify provides ability to triplicate selected design logic to reduce probability of any single point of failure. It provides ability to self-correct any single event upset or single bit errors. By auto-inserting majority voter logic at the output of TMR logic, and generate error-corrected outputs with majority voter logic. Simplify provides several TMR features, such as local TMR, block-level TMR, distributed TMR, and netlist-level TMR. Next slide, Phil. The types of triple module redundancies. There are three main types of triple module redundancy techniques. Local TMR provides register-level triplication, includes triplication for the clock enables, voter logic insertion at the output of triplicated logic. Distributed TMR provides the most comprehensive protection by triplicating IOs, clock enables, feedback logic with auto insertion of internal voter logic for feedback loops, as well as voter logic insertion at the output of module outputs. Block-level TMR provides module block-level triplication without looking into the internals of the module block and adds voter logic only at the output of the triplicated modules. Next slide. Duplicate with compare feature provides a protection with less area utilization at cost of no auto error correction. However, it does provide mechanism for error detection and lets user decide how to deploy error correction measures. You can insert error flags at the output to monitor any error by comparing the outputs. If the outputs do not match, you have the ability to reprogram or drive the error flag to design error correction logic. Next slide. Memory protection. Most larger FPGA devices have block RAM primitives with dedicated error correction check ports. Simplify can infer such memories when available on FPGA device with single-bit error correction and double-bit error detection features. You can additionally insert error flags to monitor memory block outputs, such that if a double-bit error occurs, you can simply connect the error flag to the logic block for scrubbing and memory reprogramming to fix any memory errors. Next slide. FSM mitigation techniques. There are multiple features to provide single event upset or SCU mitigation techniques for FSMs. You can enable safe encoding feature in Simplify, which will allow tool to auto-insert FSM recovery logic that takes any FSM unreachable or lock state back to reset state. Similarly, you can enable preserve or safe case FSM feature, which auto-inserts logic to ensure FSM in locked or unknown state recovers back to default or others clause logic of the state machine. Similarly, Hamming distance 3 encoding for FSM provide additional SCU mitigation techniques, which include single-bit Hamming 3 option. When enabled, tool auto inserts and builds single-bit error correction logic with Hamming distance 3 encoding. For Hamming 3 double-bit error detection option, when enabled, tool builds single-bit error correction and double-bit error detection logic with Hamming distance 3 encoding. For Hamming 3 double-bit error detection recovery option, when enabled, tool builds single-bit error correction and double-bit error detection logic with Hamming 3 encoding along with default state recovery logic for any double-bit errors. Each of these features requires insertion of additional safety logic to ensure the FSM always recovers from any unknown or locked up state. Next slide. Simplify provides you an ability to insert error monitoring flags on TMR instances, as well as Hamming 3, FSM, and ACC memory output instances. You can insert an error monitoring flag between your design error monitoring IP in the RTL and high reliability instance of your design. For example, any TMR block, Hamming 3 FSM instance, or ECC RAM instance via the FTC constraint as shown below. In the FTC constraint file, first define the instance or view of interest you want to monitor with error flag. Second, create an arbitrary error flag net. Third, connect the arbitrary error net to the high-rel instant on one side and your RTL error monitoring IP or an output port on the other side. Now run synthesis and open up the implementation netlist, and you should see error monitoring flag inserted at the output of the high-rel instance, as seen below in the right-hand side schematic view the error_flag port. Okay, next slide. Per DO254 guidelines, Simplify provides results that are traceable, repeatable, and equivalent. We can trace synthesized design results via netlist schematic, timing reports, log files, for safe FSM and TMR implementation via high reliability report. Results that are repeatable by reproducing synthesis results with same project option and constraint settings. Lock down pre-verified blocks for any re-optimization via synthesis attributes and directives. For equivalency, Simplify provides scripts for RTL and netlist level simulation, comparison, and preservation of sequential elements for equivalency check, and also provides probing, tracing, and implementation of hierarchical design signals for debug visibility. Thank you. Back to you, Phil.
Thanks, Khaled. So now let's look at some of the key takeaways from the presentation. The first is that Lattice, together with Synopsys, has put together an optimized team-based design flow that can help reduce the FPGA design cycle by increasing the efficiency of your FPGA design team. It enables you to create reusable results, and it can reduce both the simplified synthesis time as well as meeting the needs of secure and safety critical design flows. In addition, Simplify with their Simplify Elite product provides high reliability design flow benefits for safety critical designs. So thank you for attending today's presentation. We will now open it up to questions and answers. So the first question that's come in is regarding the floor planning in the team-based environment. It says, is it recommended to floor plan all of the blocks in the design? So you can floor plan all of the blocks in the design. However, we really recommend that you only floor plan what you really need to floor plan. So in the case of an isolation design flow or safety critical, that would be the portion of the design that you would have to floor plan. In the rest of the designs, we really recommend that you'd only floor plan the timing critical blocks to preserve the timing on those blocks. By leaving the others as unfloored plan, it provides a lot more flexibility for the place and route software to provide you with great results. But you can floor plan the whole device and have all of the blocks integrated, and the tool will support that. Next question. Is the Radiant software ISO 26262 certified? So the software today, the Radiant software today is not ISO 26262 certified. However, the version 22.1.1 version of the software will be ISO certified in the first quarter of 2024. And the Simplify, correct me if I'm wrong here, Khaled, but I believe the Simplify software, the Simplify Elite, is certified.
Correct. The older version of the tool is certified, so we're doing recertification for the 2022-09 release coming out in January.
Okay. Next question is regarding the high reliability version of Simplify. It says, when will this version support the Avant devices?
So the actual TMR support has been enabled for quite some time. I would say 6-7 years ago. For in particular to Lattice devices, the latest upcoming release of 2023-09 in December, it should have all the supports for Avant, Certus Pro, Crosslinks, and Max X05 devices as well.
Excellent. And a follow-on question on that topic. What's the cost for the high reliability version?
So cost in terms of area, or is it in terms of the actual pricing of the tool? So pricing of the tool, please do reach out to us, and I can have somebody from our account management team to reach out to you and set up a call. In terms of area utilization, yes. So anytime you triplicate your modules, you're taking the 3 times the area. So the recommendation is that do local TMR or do netlist level TMR. You can run the first pass synthesis and get an optimized version of your netlist, and then do TMR on top of that on selective design components that are critical for safety and reliability.
Okay, next one is, when is the block-based flows supported in the Radiant tool? So the 2023.1 release of Radiant was the first release to support the block-based or micro-based design flow. The 2023.2 release, which has just come out, has added additional capability to the block-based flow, including the support for the safety critical design flow and some usability enhancements. Next question is, does the flow support multiple isolation regions? So it is possible to have multiple isolation regions in the design. It really comes down to the designer as to how they want to structure their design or what their requirements are, but there is no restriction from that perspective in the tools. Next question is, what level of granularity is available with the TMR feature?
Yes, so as discussed on slide number 22, I believe, so there's different types of TMRs where you can do a local TMR, where you can do a register level TMR, or a block level TMR where you can take the entire module block and triplicate it, or distributed TMR, which is more comprehensive, that does internal logic of the block as well as the output of the block and serves the motor logic. So it really depends on what level of protection you require. The more logic that you utilize, the more protection you get. The less logic you utilize, the less the protection. So it's all about area utilization versus safety. How critical is your safety for those blocks in your design versus how much area do you want to utilize?
Great, thanks, Khaled.
Sure.
And that's the questions we have for today. Please do continue to provide your questions, and we will get back to you with the answers.
All right. Thank you.